What we're going to do now is we're going to take a look at JPEG, which is, I was going to say GIF's main competition, but there isn't even really a competition. JPEG is by far the most popular image format in the world right now, and the most popular that has ever been. Okay. JPEG stands for Joint Photographic Experts Group, and there's no dispute about how to pronounce JPEG. It's JPEG. No. So, way back you had GIF, and you also had TIFF. I remember encountering Sun raster file format as well, which was an image format on Sun computers. On Microsoft Windows you have PICT. So generally, if you were designing a computer system, because it probably wasn't connected to anything else anyway, you could make up your own image format and everything would be fine, because the images on that computer had to be displayed on that computer and everything was grand. However, once computers came to be connected to each other and images were stored digitally, people had an expectation that they would be able to share them. So if I had an image on my computer and then I sent it to you, it became a huge source of frustration that you couldn't open it, that you had to maybe go get some special piece of software that might convert it to a format that was usable on that computer, and that's if you could find one. And so the International Standards Organization decided that maybe there was some work to be done on coming up with an image format that would be standardized. And then the standard could be published, and then people could save images in that format, and they could, write their programs that could open them up and whatnot. So it was ISO standard 10918-1 is what we eventually got. And it took a few years. And so the format then that was decided upon was kind of state of the art, something that made a lot of sense for the technology of the time, which was 1992. Now, as you can imagine, 1992 was a long time ago in computing terms. Among the earlier supporters of JPEG was the California DMV. So they would have had people's digital pictures stored for their driver's licenses, but they were in some freaky format that couldn't be shared. So if the police in Louisiana wanted someone's picture, they would have a digital copy of it in color. They would probably end up printing it out and then faxing it to them or something. If they were to email it to them, then if they had email, it might turn out that, they couldn't actually open it because it was in some weird format. I remember even when I was working in WIT, not a million years ago, the student ID cards, you saved the students' pictures in a different format, in some strange format that couldn't be opened in anything else. And I think the company that made the software would sell you then, for extra price, would sell you to have them in JPEGs if you wanted. So it's hard to imagine in 2015 what I'm even talking about. Of course, if you're going to have images, they have to be in some standard format that you can, swap with people. How is that even a thing? But in the 80s, that was a thing. There were lots and lots of different formats, and it was a lot of trouble. So, I have mentioned lossy and lossless compression before, but it's worth talking about them again just to jog your memory. So with lossless compression, if you take an image, compress it, or transmit, send it, and then at the receiving end, you decompress it. If the decompressed version is an exact replica, like exact pixel per pixel, value for value, exactly the same, then the compression is lossless. There's no loss. If it's not exactly the same, then it's lossy. And it turns out, for various reasons, mostly due to the fact that human vision isn't that good, we're able to tolerate quite a lot of loss in our images without getting upset. So JPEG is typically lossy, but it can actually be lossless. JPEG does have a lossless option, but people talk about JPEG as being lossy. So someone say to you, GIF is lossless and JPEG is lossy. Well, kind of. As we've seen, GIF is lossless, yeah, but you know, you're down to 256 colors, duh, and JPEG is 99.999% of the time used in a lossy way, but it need not be lossy, okay? So when it comes to compression then, we have to deal with this cost-quality trade-off. So if you have the image quality as high as it can be, if the image is perfect and there's no loss, well, that's great, but the image file is going to be big. On the other hand, if you reduce the image size way down low, you get a nice small image file, but the quality might suck. So you have this trade-off. You can have large file size and big quality, or small file size and low quality. Now it turns out that's not really linear. Do you know what I mean? That you know, 50% of the file, like halving the file size, doesn't half the quality. Whatever halving the quality means. I'm not sure what that means. I mean, could I show you one picture, another picture, and you would say, you know, this image is half as good as this one? I'm not sure how you could measure quality in that way. We do have, I mean, if you're doing experiments, you do have a way to actually measure the loss, but from a subjective point of view, what does half as good mean? Who knows? So when you're saving images and you are introducing some loss, you want to have a look and see subjectively where's a good point, a good sweet spot, where you have a good cost-quality trade-off. JPEG is a very good example of that, in that if you go into Photoshop and you save something at 100% quality, it'll look great. If you save it at 80% quality, typically it'll be half the file size, and you won't be able to tell the difference, typically. So you might not be able to see the difference between 100% quality and 80% quality, yet you have the file size. And although images download really, really quickly now, so from a user's point of view, it's not such a big deal. If you're at the server side of that, and you're a business, or you have a web page, you're paying for hosting. So, I mean, my plan is not pay as you go. You know, I would have to pay more if more people looked at my web page, but so few people look at my web page that I don't actually hit my limit. But if my websites were more popular, I would end up paying more. And it's crazy to pay twice the amount for each image that someone downloads when, you know, there's no need. So you do have to work with that. So when we talk about the compression ratio, then we typically have the uncompressed size over the compressed size. So you might have a compression ratio of 4, or 4:1, you might call it. No. So you can have high quality and large files, or low quality and small files. So again, it depends on the situation. For example, if you're going to the gym, you might decide, you know what, I would sooner have 400 songs on my phone at not great quality rather than 100 songs in really good quality. Now, if you're hooking something up to your stereo, if you like come into some money and you spend $1,000 on a stereo, you might decide, well, no, I'm not going to use low quality there. That would be a shame. I'll go for the high quality files. But for the gym, probably more at low quality is better. So depending on the context of the situation, it can vary. Pictures of you in the pub, you might decide, I don't want them taking up too much of my hard disk, I'm going to compress those down a bit. The pictures you took of your firstborn child, you probably keep it high quality. Your wedding pictures, you're not going to, shrink down nice and small. Okay? We already talked about luminance and chrominance when we were looking at the LAB color system. But this really comes into play in JPEG. So I think I mentioned already that human vision is less sensitive to chrominance than it is to luminance. So we have rods and cones in our eyes, and we have many more rods than we have cones. So we're very sensitive to subtle changes in lightness and darkness, but subtle changes in color, not so much. So JPEG subsamples the color component of an image and leaves the luminance part intact. So that's one of the tricks JPEG does. So there's loss there straight away. You're losing some of the color information. So in this image here, you see we have the luminance information and we have the chrominance information. Here I've subsampled, well, here I'm showing you again. We have the original image here, and here's some luminance information, and here's the A channel and the B channel. So this is the A channel, this is the A channel subsampled. You can see there in the subsampling, the pixels have gotten much bigger. Here's the B channel and the B channel subsampled. And I combine the A and B channels back together, and so here the chrominance information has been subsampled. So there's a lot less color information in this picture than there used to be. And I don't think we can really see the difference. I'm just looking really, really close there. At the bottom right of the bottom tile, I think some of the blueness has come off that tile and is appearing in the brick. It's very subtle. I don't know if you can even see it. But some of the blue has kind of come out of its box, so to speak. But you'd have a job to see it, really. Okay? So, JPEG works on 8x8 blocks of pixels. So if you have an image that's 800 pixels by 800 pixels, JPEG is going to break that up into 8x8 blocks. Okay. Now, looking at it today, you could say, you know what, 16 by 16 blocks might be better. But back in the 80s and 90s when this was being devised, computers were a good deal slower. And we end up doing quite a bit of maths on those 8x8 blocks. And the maths that was being done wasn't linear. So a 16 by 16 block certainly would have been twice as much work, but it wouldn't even have been 4 times as much work. It would have been a lot more work. And so it was decided that maybe 8x8 blocks were the way to go. Okay, so then each block then is worked on individually. When the quality of the JPEG is too low, you can actually see the blocks. You can actually zoom in and you can see that's one 8x8 block there, that's the start of the next 8x8 block there. The blocks actually become very, very visible, very evident. Okay? Now, so it's quite an elaborate process and I'm going to explain it to you without the actual maths, okay? So there's this thing called the discrete cosine transform, which, if you know about these things, and I don't really, is a special case of a Fourier transform. And what this does is it essentially beams up the information from the spatial domain to the frequency domain. So the 8x8 block of pixels, that's information in the spatial domain. And the discrete cosine transform transforms that data to the frequency domain, it's called. Once it's in the frequency domain, you can do an inverse discrete cosine transform and beam it back down to the spatial domain. So it's this thing you can do, and it's reversible. A very important point about the discrete cosine transform is that it's completely reversible and lossless. Many people will tell you that the discrete cosine transform is lossy, but the discrete cosine transform itself is lossless. So you can do the DCT and do the inverse DCT and get back exactly what you started with. Okay? So I like to think of it like Star Trek, where you get kind of beamed up, you're in some place before you arrive at your destination, and then you get beamed back down again. No. So I've populated these values here with some numbers, just so we can see what's happening numerically, but I don't want to get too hung up on it. Okay? So these values here, we are doing the discrete cosine transform. No, sorry, the first thing we do is we subtract 128 from each one. So these would have been values between 0 and 256. So now they're values between minus 127, I guess minus 128 and 127. Okay, so the middle point is 0. No. With these values then, we do the discrete cosine transform. And I won't show you what the discrete cosine transform is or what it does, but you can look it up. But it's this big maths thing, okay? And what you end up with when you take all this data here and you do the discrete cosine transform in it is you get these values here. Now, what's interesting is that you always get this huge, very significant value here in the first place. In the first slot, you get a very big value. And then if you look at the remaining values, you can see they're kind of biggish at this end and kind of smallish down this end. Like, whereas the values here were pretty much spread out all over the shop. You know, big, small, they were, you know, spread out everywhere. Here you get this big, huge value at the start, and then you've biggish values in the top left, and as you get closer to the bottom right, you get smallish values. And that always happens. That's not just the set of numbers I chose there. That always happens with the DCT. Okay? Now, the next thing we do then, all right, is we do what's called quantization. And each of these values here gets divided by a particular value. And we have a grid here of 8 by 8. And what's interesting here is that this choice of values needs to be good for the JPEG to work out well. But who's to say this should be 16 and not, 17 or not 14? And it turns out actually that this choice of values is often unique to a particular implementation of JPEG. So if you encounter a photograph that was converted to JPEG, often you can analyze the photograph, analyze the values chosen, and you could say, haha, this was taken with a Nikon D90, model whatever, and therefore the killer must be, whatever. So you can actually do a bit of CSI stuff on the values chosen here. But if you look, this is quite a big value here, and that's because this is a big value. These are reasonably big, getting very big down here. And we'll see what happens now. So we're going to divide this by this to give us something. We're going to divide this minus 30 by 11 to give us something, and this minus 61 by 10 to give us something. Okay? So you see what's going on there? Okay? Now that part of the process is lossy, because if I divide minus 30 by 11 and get minus 3, I can go back by multiplying by 11, but I'll end up with minus 33. I won't get back exactly what I started with. So this quantization part here is what's lossy. That's what's introducing the loss. And so we keep going here, and so on. Hopefully I haven't made any mistakes. Whoop. And we get something like this. Okay? Now, if we look at these values, look what's happened. So the small values got divided by big numbers, and we ended up with zeros. The not so small values got divided by not so small numbers, and we ended up with a lot of minus ones and twos and things. Okay? And you can see that there's all this information here that's quite compressible. Can you think how we might compress this? Well, run length encoding might work for all these parts here. So actually what we do is we go in this zigzag pattern here. So we do this value, then this value, then this value, then this one, 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 and 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 this one. And so by the time you're done, you get a set of values that's actually very easily compressed. It's very compressible. And so you can save those values, you can transmit those values. When they get to the other side, you can just do the reverse of the process. So you can do instead of dividing, you can do your multiplying, and you get back, these values here. You can do your inverse DCT and get you back those, and you can do your add 128 and you get back your values. So they're all reversible steps, although one of them is certainly lossy. Okay. So the long and the short of it then is that it turns out that JPEG is best suited to natural images. So photographs of people or of scenery, clouds, grass, trees, nature. JPEG's great at those. Where you have plain expanses of color, or where you need crisp, sharp color, it's not so good. So just to recap then, so the discrete cosine transform will take your image data and transform it to the frequency domain. And then you can get it back down again to the spatial domain again. And that in itself is lossless. But what we do, you see, is when it's in the frequency domain, we subsample that data. And that results in some loss. But when we beam back down, the difference isn't huge. So imagine if you had me in the spatial domain and you said, Colin, you know, you're a bit too heavy, we need to lose 10% of you, so you chopped off my arm. Okay? That's getting rid of data in the spatial domain. Pretty drastic, pretty noticeable. On the other hand, if you beamed me up to the frequency domain and you said, okay, Colin, we're going to get rid of some of you there. And so you got rid of 10% of me in the frequency domain. When you beamed me back down, you might go, oh, Colin, you look like you've been to the gym, you've lost a bit of weight, you know, a bit pale, but you know, hey, you've got 2 arms, 2 legs. So when image data is in the frequency domain, we can target the stuff, the very stuff that humans don't really notice so much. So the stuff we don't see very well is what we actually throw away. And so when we beam it back down, we hardly notice the difference. Okay? So some of the problems though, when the compression ratio is very high, you actually see those 8x8 blocks of pixels. So JPEG isn't great where you have crisp edges or plain expanses or big expanses of plain color. So where you have fine lines and detail, it can start to give way. So if we zoom in here, well, even at this multiplication, you can already see the blocks. Can't you? When we zoom in, you can actually count up the pixels. Does it go any further? Yeah, look. You can actually see it's 1, 2, 3, 4, 5, 6, 7, 8 by 8 blocks of pixels. Because it takes 8 blocks, 8 pixels, does its thing. Next 8 by 8 block does its thing. Next 8 by 8 block does its thing. And so if something is in more than one block, the transition from one block to the next isn't always smooth. And so you can see what's going on there. It's actually easier to see here, I think. Yeah? Okay, so that's JPEG. So depending on the situation, JPEG may be preferable to GIF, or GIF may be preferable to JPEG. I forgot to mention that one of the main compression schemes GIF uses is Lempel Ziv Welch. It takes groups of pixels. So if a pattern kept repeating in a GIF, it would do very well compression-wise. Okay. Any questions on that? So that's GIF and JPEG. So all we have to look at next then is PNG.